Hello, in this video we introduce matrices and how to compute the transpose of matrices. A matrix is an array of numbers like the one you can see on screen. So it is numbers that are ordered in a certain amount of columns and of rows. For example, the matrix that you can see on the screen has 4 columns and it has 3 rows. So we can say that this matrix is a 3 by 4 matrix because we put first the number of rows and then the number of columns. So again, this matrix has 3 rows. The first one is made of the numbers 2, 5, 7 and 2. The second one is made of the numbers 3, 1, 8 and 5, and the third row is composed by the number 5, 3, 7, 1. The first column has the numbers 2, 3, 5. The second columns has the numbers 5, 1, 3. The third column has the numbers 7, 8, 7. And finally, the fourth column has the number 2, 5, and 1. We can generalize how a matrix is written in this way, where you can see that A is a general number and the subscript with the numbers, for example 1, 1 or 1, 2, refers to first the number of the row and second the number of the column. This is still a 3 by 4 matrix. Now let's consider a 3 by 3 matrix, which means that it has 3 rows and 3 columns. So when the number of columns is equal to the number of rows, then we can say that the matrix is squared. It's a squared matrix. So in a square matrix, we can define a diagonal which is made of these elements, the elements that have the same numbers in subscript, so they have the same number of column and number of row, which are A11, A22 and A33. And this is the diagonal of this squared matrix that is a matrix 3 by 3. Now let's consider this matrix and we want to compute the transpose that is indicated by a t, a small t at the top right of the matrix. We want to compute the transpose of this matrix. The transpose of this matrix is also another matrix where the numbers have a different order. In particular, let's consider the diagonal. What happens in the transpose is that the number A21 takes the place of the number A12, and the number A12 takes the place of the number A21. In the same way, the number A31 takes the place of the number A13, and the number A13 takes the place of the number A31. And again, the number A32 takes the place of the number A23, while the number A23 takes the place of the number A32. And diagonal numbers are always in the same place. So the transpose of this matrix is this matrix. And it's important to notice that the transpose of a squared matrix is also a squared matrix. Now let's see a numerical example. So let's assume that we have this matrix. It's a 3 by 3 matrix, 3 columns and 3 rows, and we want to compute the transpose. The transpose of this matrix is this matrix, and now we see why. So we can see that the diagonal numbers are the same, 1, 5 and 9. Then we have the element 2, 1 of the matrix, that in this case it is the number 4, takes the place of the element 1, 2. Then we have that the element 1, 2, which is a 2 in this example, takes the place of the element 2, 1. Again, we can also do this game for the other numbers. We have the element 3, 1, which is the number 7, that takes the place of the element 1, 3. So it goes here. And again, the element 1, 3 takes the place of the element 3, 1. so forth and so on. So we have understood how to compute the transpose of a matrix. But we are only working for now with squared matrix. What happens when I want to compute the transpose of a matrix that is not squared? For example, this is a matrix that is 3 by 2. So we can indicate it as a letter M and the subscript 3, 2, because first we have to put the number of rows and then the number of columns. So if we compute the transpose of this matrix, we have that the first column, 1, 4, 7, becomes the first row of the transposed matrix. In other ways, we can also see that the first column of the matrix, which is, the first row of the matrix, which is 1, 2, becomes the first column of the transposed matrix. So, the transpose matrix is a 2 by 3 matrix. So we can generalize this rule saying that the transpose of a M by N matrix is a N by M matrix. Or we can also write it in this way. Okay, now we have seen how to compute the transpose of matrices, and we can try to practice a little bit. And we can practice with the exercise 1. In particular, we do the exercise 1.1 at page 64. So we have to find the transpose of the matrix A, which has 2 columns and 2 rows. So it's a 2 by 2 matrix. So to find the transpose of this matrix, we have to remember that the first row of the matrix A will become the first column of the matrix transpose A. Or another way of saying, the element 2, 1 will take place of the element 1, 2, and the element 1, 2 will take the place of the element 2, 1. So we can write the transpose of the matrix A in this way. You see that the elements that are in the diagonal did not change their position. So the A is a 2 by 2 matrix, and also its transpose is a 2 by 2 matrix. Now let's go ahead. We have to find the transpose of the matrix B. B is a 3 by 3 matrix because it has 3 rows and 3 columns. When we want to compute its transpose, it's very useful to first start from the diagonal elements, because we know that in a square matrix, the diagonal elements in the transpose matrix will have the same location of the original matrix. So we can write them down, 1, minus 1, and 7. Then the first column of the matrix B will become the first row of the transposed B matrix. And so you see that in the first columns of B we have the elements 1, 2, minus 4, and they will appear in the first row of the transposed matrix, 1, 2, minus 4. In the same way, the elements that were in the first row in the B matrix will take the place of the first column in the transposed. So in the first row we see 1, 5, minus 7, that will become in the first column, so 1, 5, minus 7. Okay, we can play the game again. So the second row of the matrix B will become the second column of the matrix transposed, and so forth and so on, so that the final transposed matrix is this one, which is also a 3 by 3 matrix. Now we have to find the transpose of the matrix C, which is a 2 by 2 matrix. This is quite easy because all the elements that are not in diagonal are the same. So its transpose is simply this matrix, where we see that the diagonal elements are still the same, 0, 0, and also the other two are equal because they are equal. They are two equal numbers, 1 and 1. So the transpose matrix in this case is equal to the original matrix and is also a 2 by 2 matrix. Next one, we have to find the transpose of the matrix D. The matrix D is a 3 by 3 matrix. It has the numbers 2 on the diagonal and 0 everywhere else. When we write its transpose, first of all we write all the 2's on the diagonal because they will not change location. And then we have that the first row of the matrix D will become the first column of the transpose matrix D, and so forth and so on. So the first column of the matrix D will become the first row of the transpose matrix, so forth and so on till we compute the complete transpose. Also in this case, since all the elements that are not in the diagonal are all zeros, the transposed matrix D is the same of the initial matrix D, and it's also a 3 by 3 matrix. Okay, now we have to find the transpose of the matrix E. This matrix has 4 rows and 4 columns, so it's a 4 by 4 matrix, and we have to find its transpose. So let's start from the diagonal elements because they will not change their position, so we can write -1, 7, 1 and 10 in the same position as in the original matrix. Then we can take the elements in the first column of the matrix E and write them in the first row of its transpose. And it will appear like this, -2, 5 and 7. Then we have that the elements in the first row of the matrix E will appear in the first column of the matrix transposed. So 9, -3 and 7 will appear here. If we go ahead, we find that the 4 and 6 will be on the second row of the transpose matrix because they were in the second column of the original matrix. We have that 5 and 4 will appear in the second column of the transpose matrix because they were in the second row of the original matrix, and so forth and so on to complete the transpose matrix, which is still a 4 by 4 matrix. So by now we have only seen transposed of squared matrix, so that where the number of columns is equal to the number of rows. And now we can do some examples where we don't have square matrices, and this is exercise 1.2 at page 64. So we have to find the transpose of the matrix A, and its transposed, it's a matrix, is this matrix. So when the original matrix is a matrix 1, 3, the transpose is a matrix 3, 1. So if in the original one I have 1 row and 3 columns, in the transposed one I will have 3 rows and 1 column. Next example is the matrix B, 1, 5, 3. The matrix B has 3 rows and 1 column, so it's a 3 by 1 matrix, and its transposed will be this matrix that has 1 row and 3 columns. Next example, we have to find the transpose of this matrix. This matrix has 2 rows and 3 columns, so its transpose will be a matrix that has 3 rows and 2 columns. In this way, you can see that the first column in the matrix C it has the elements 3 and 2 that now are located in the first row in the transpose matrix. In the same way, -4 and 5 that are in the second column of the matrix C appear in the second row of the matrix transposed. Finally, the elements 1 and -6 that are in the third column of the matrix C appear in the third row of the matrix transposed. So the matrix C is a 2 by 3 matrix, and the transpose is a 3 by 2 matrix. Now we can also try the next example. The next example is the matrix D. This matrix has 3 rows and 2 columns, so the transposed matrix will have 3 columns and 2 rows. And we see that the elements 2 and 9 that were in the first row of the D matrix are now in the first column of the transposed. The elements 4, 3 that were in the second row of the D matrix are now in the second column of the transposed. And the elements 6, 7 that were in the third row of the D matrix are now in the third column of the D matrix. So the D matrix is a 3 by 2 matrix, and its transpose is a 2 by 3 matrix. Next example is the matrix E. This matrix has 2 rows and 4 columns. Its transpose will have 4 rows and 2 columns. we can see that the first row of the matrix C has the elements 2, 3, 4, and 5 that now appear in the first column of the transpose. In the same way, the elements in the second row of the matrix E appear in the second column of the transpose. So the matrix E is a 2 by 4 matrix and its transpose is a 4 by 2 matrix. And this is the end of this video.